Okay. So now let's start in the tricky lecture. I hope you are still awake. It's composition of state machines, which is chapter 5. We have the actor model for extended state machine, which has inputs and outputs. Sorry, 1 second. And we have the guard as shown here, the output action and the set action. So the first, we are in this chapter composing the state machine, which might consist of smaller state machines. So the first composition is side by side, which is clear from its name. We have input that leads to output, I1 leads to output 1, and I2 leads to output 2. And the C state machine consists of two subsystems or two similar state machines, A and B, and this is called the side-by-side composition. Here, the state machine being composed don't communicate with each other in the side-by-side composition, and the input and the output are disjoint. And we have two types of composition: synchronous and asynchronous composition. When you hear word synchronous in circuit, what does that mean? Sorry? Exactly. It's like, did you study latches and flip-flops? There is a clock that feeds the latches or the flip-flops, and at the same time, they move together. So this is the synchronous from its name. They exist at the same time, moving and operate at the same time. So in synchronous composition, components A and B react simultaneously in a globally synchronized step. Each transition of the composed system correspond to joint transition of A and B. And as I give you an example in circuits, it's like a clock that drives the flip-flops or the latches. Also in power systems, we might have this synchronous word, which means it has the same frequency and phase, the electrical waves. Now, can you explain what will happen in this state machine if the composition is synchronous? The, the transition is from S2 to S1 that output A, right? Exactly. Thank you so much. So to repeat what your colleague said, so we have S1. We start. This is the initial start, S1 and S3, and upon the first time step, we transition to S2 in component A, and transition to S4 in component S4, and they happen simultaneously at the same time because this is synchronous composition. And then at the second time step, we go from S2 to S1 and output A, and from S4 to S3 and output nothing. So now the A and B, the components A and B are happening simultaneously. Do you agree? Because they are synchronous. What about the output A and B? Are they output? Are they available in a synchronous fashion? How they? What's the shape of the output? Exactly. Why? Exactly. So here, don't confuse yourself with the output A and the component A. The component A and B are happening together. However, the output A and B will one be absent and the other will be present. And this is according to the condition inside the system. It's not something that's available in all synchronous state machines, just in this example. Because from S1 to S2, which is the first step, we output nothing. And from S3 to S4, which is the first step, we output B. And then, so the B will be present and the A will be absent. And then when we go back from S2 to S1, we will output A and the B will be absent. So the A and B are oscillating. Do you agree? Okay, great. So such composition are modular in the sense that the composition has a component inside uh, inside it until you reach an atomic component. So each system has a component inside it. For example, the C has A and B, and the A and B are atomic components. And the state machines are deterministic. If the two state machine are deterministic, the synchronous site composition will be also deterministic. And if the property is compositional, then the components also will carry the same feature. So for example, if we say the C has some feature, then the A and B will carry the same feature. And then what's the difference between syntax and semantics? Exactly, the syntax is how to write the notations, and the semantics is the meaning of the syntax. And our syntax is state, input, output, update, and initial state. And inside the state C, we have what does X mean? Exactly, Cartesian product, which means all subsets between A and B. You take component from A with B, and you consider all the combinations in the new composition C. And in the inputs also you consider all the combinations in the output, and in the initial state you just combine them. In the update you will have update A, which takes the current state and gives you the next state, takes the input and gives you the output. And the update C will take the state input, the two states of A and B, the two inputs, and give you the next state and the two outputs. And the Cartesian product means all subsets of inputs A with all subsets of inputs B. Now the first bonus question: can you write a single state machine that describes the semantics of this synchronous composition? It's not an easy question, but yeah. So S1, S3, okay. And then 1, 4, 2, 3, and 2, 4, okay. If we have true here, we go to 2, 4, okay. And output B, okay. So we will go back and output true. If we got true and output A, okay. Okay. Thank you. Yeah, this is called non-reachable states. You can either plot it and not plot it. You are right. Yeah, thank you. Ex- Exactly. You can avoid drawing S1, S2, S1, 4, and 2, 3. Do you have other opinions? Why we consider 1, 3, 1, 4, 2, 4, 2, 3? From what? Okay. Okay. Thank you. Do you have different opinions? Yeah, okay. But why we consider 1, 3, 1, 4? Why not consider only S1 and then S3? Yeah, thank you so much. So if you go back to the definition of the composition, the state of the composition is the Cartesian product of A and B, which all the subsets of A and B. That's why I consider 1, 3, 1, 4, 1, 2, 4, all possible combinations between elements from A with elements from B. So this is the definition of Cartesian product. That's why I consider all the combinations. And then why is 2, 3, and 1, 4 are non-reachable? Exactly. Thank you so much. Is it the same reason, or do you want to add something? Okay, because as she said, it is synchronous. Yeah, exactly. Thank you so much. So the answer is correct. So we have two separate state machines, S1, S3. So we consider all combinations from state 1, from component A and component B. So we have 1, 3, 1, 4, and we didn't consider 1, 2, right? Why? Why I didn't consider 1, 2 yet? Exactly, because also the formal definition is states from A with states from B. You cannot take A with A. It doesn't make sense to be at 1 and 2 at the same time. That's why we didn't consider the 1 and 2 in one state. And then as they are synchronous, like the circuit, they are happening together. So at each tick or each clock, we have an action on the component A and action on the component B. So in the beginning, we are at S1, S3, which is here, S1 and S3, the both initial conditions. And then upon the first tick, we have true going to S2, and we have true also going to S4. One is outputting B, and one is outputting nothing. That's why the combination is true and B. And then from 2, 4, we have true back, which is true in both cases, which is true here. And one is outputting nothing, and one is outputting A. That's why it's A in the output. And given that they are synchronous, you cannot move in one of them and pause the other one. They are happening together. So if you are, it's either S1, S3, or 2, 4. That's why the two other states are non-reachable. If they are not happening together, they will be reachable. And as you can see, the components A and B are happening together. However, the output are oscillating. A, B, A, B. Right? Don't confuse yourself. The behavior of the synchronous means they are happening together, but according to this example only, the output is oscillating. Small a, small b, oscillating. Is it clear? Okay, great. Thank you. And I wrote here SC equal the Cartesian product from SA to SB. And S1 and S4 and S2 and S3 are not reachable states. You cannot reach them if you start from the initial condition. So now let's make it more difficult and have asynchronous composition. In asynchronous composition, the components react independently. They are not reacting together from its name. And we have two types, either semantic 1 or semantic 2. The semantic 1, the reaction of C is a reaction of A or B, where the choice is non-deterministic. So either A will respond or B will respond, but the choice of A or B is non-deterministic. This is asynchronous. They don't cooperate together from its name, right? And we call this semantic interleaving semantic, meaning that A and B never react simultaneously. Their reactions are interleaved in some order. So either A reacts and B remains idle, or B reacts and A remains idle. Is this clear? Clear for everyone? And then semantic 2, the reaction of C is a reaction of A, B, or both A and B, where the choice again is non-deterministic. It's a variant of this possibility allow neither of them to react. So if I would like to comment on the difference between semantic 1 and semantic 2, semantic 2 generalize semantic 1 by allowing a reaction to consist of A only, B only, both A and B, and in some definitions, no reaction at all. This is semantic 2. Is it clear? So we are composing state machines, and we are studying the semantics of combining the state machines. I asked ChatGPT to build a table for the difference between synchronous, asynchronous semantic 1 and semantic 2, and it answered very well. So every column is one type. So the execution model of the synchronous, as we have learned, it's synchronized. Every subsystem or process performs a computation step simultaneously at each discrete time tick. So this is the first synchronous composition, which we have studied the semantic for it. And as you can see, the reaction of C is simultaneous reaction of A and B. The C contains the A and B. And then the asynchronous semantic one, which is the interleaving, one component react per step, either A or B. And the choice of who reacts is non-deterministic. It might be A, or it might be B. This is the interleaving semantic. And semantic 2, it's a generalization of semantic 1 where it allow A or B, both A or B, or neither of them in some definitions. And again, the choice is non-deterministic. Is it clear? Yeah. Okay, great. So before I start here, maybe let's take a break until 1:45. Thank you. So let's continue. So if you remember before the break, we talked about this nice table from ChatGPT that summarizes what we have learned so far: the synchronous composition, the asynchronous, and the semantic one, interleaving, and semantic two. In the synchronous, we have both A and B act simultaneously. In the semantic one, asynchronous, we have one component reacts per step. Only A or B reacts in a non-deterministic fashion, and in semantic 2, A, B, or both, or neither of them in some definitions react, and the choice is non-deterministic as well. Now, as a bonus question, can you give the asynchronous semantics using interleaving composition? The choice is non-deterministic. The choice of A and B is non-deterministic, right? Okay. It, it's deterministic. The choice of A and B is non-deterministic, but the state machine is deterministic. So maybe I can draw with you. So what should I draw? Awesome. So 1, 3. So in one state, all of this? So, but you can have it in two transitions, either go here or go there, right? It's still deterministic. Yeah, maybe just do it step by step and then we discuss. So what should I write? Okay, 2, 3. And what would be the transition? And the output? Okay. Oh, this why you mean it's non-deterministic because upon the same input it goes to different states. Yeah, okay, it's acceptable. Yeah. Sorry, from where to where? Uh, 2, 4. Okay. Okay. From where? From where? One, 4 to 2, 4. true and nothing. Okay. Yeah, thank you. Do you want to change anything? Okay, do you agree to this or do you want to change anything? Agree? Okay. Anyone would like to add anything? Okay. I think it's correct. Except I think there is a mistake only here, which is minor. From 1-3 to 2-3. Oh, it's just swept, but it's correct. Yeah, correct. Okay, great. Thank you. So let me explain it. So we said that we are in the asynchronous composition, right? Which means A or B react. This is the interleaving semantics. So as a high level check, any move from 1-3 to 2-3, any move on any arrow should lead to change of one state only. Do you agree? Can I change it from 1-3 to 2-4? No, because this will lead to changing S1 to S2 and S2 to S4 and S3 to S4, which means I am changing both states at the same time. So it's as a high level check, as I mentioned, it's only one digit change, if it's okay to call it digit. For the first digit is for A, and the second digit is for B. So the first change is only changing S1 to S2, and the second change, for example, is changing S3 to S4. So this is a high level check that we are in the correct direction. And then let's check one by one. So we are at S1 and S3, and true happens. Let's assume first the A reacts, which means 1 will change to 2. So 1 will change to 2. And 3 will remain the same. So 3 remains the same. And we will output A, because from 1 to 2 there is no output. Sorry, we will not output anything, because from 1 to 2 there is nothing. And 3, if you stay at 3, you're not outputting anything. Right? And then if you go back, let's maybe take the other direction and consider we are at S1, S3, and B reacts instead of A. So if B reacts, then the 3 will become 4. The 3 will become 4, and S1 will remain the same. Do you agree? So S1 will remain the same and S3 will change to S4, and we will output B because upon changing from S3 to S4 we have the output small b. So this was the first step, and then you can take any change, for example from S2 S3, and A reacts, which means the S2 become S1, and we keep S3 as it is. And or S3 changes to S4 and we keep S2 as it is. And then at S2 S4 we keep S4 as it is and change S2 to S1 and so on. Is it clear? What's the difference between this and the previous one? As a high level note. This is synchron, yeah. But it's still there is a tick, but the difference here, both of them should react simultaneously. Do you agree? So here I am at S1, S3, and both digits change at once. The S1 becomes S2 and the S3 becomes S4. But and if you would like to change one only, it's not reachable. If you would like to move from S1 to S3 and only keep S1 and change from S3 to S4, which means the A will not react because you stay at S1, and S3 will change to S4, which means B will react. This is non-reachable. There's no transition because both of them reacts. So this is a high level note on the difference. Here we are changing the two digits at once, and if we go back or move forward to this, here we are changing one by one. S1 change it to S2 and we kept S3, and then we kept S2 and changing S3 to S4, and then S2 change it to S1 and we kept S4, and then back we changed S4 to S3 and kept S1. Is it clear? Okay, great. Clear for everyone, or? Yeah. Okay, great. And here note that all states are non-reachable, and it becomes, as you mentioned, the semantics become non-deterministic. But here it was deterministic state machine, right? But the semantics become non-deterministic, as a note on that also. And then another bonus question: what are the changes to satisfy semantic 2? You don't need to do the self loops because if you are not outputting anything. from S1 to SS3 for S1 SS3, if you are at S1 and SS3 and then you would like to change both at the same time, you will add a transition to S2 S4 as you mentioned. So upon this you are getting true, so A and B will react simultaneously and you'll have a transition like this. But let's check the other direction, S2 S3 and then 1 4. Yeah, you can have this also because, but you will you reach this? Yeah, you can reach it. Yeah, you are right. Exactly. So you can. It would be possible to move from S1 to for S1 S3 to S2 S4. You can add also. You can move from S2, as your colleague said, S2 S3 to S1 S4, or make it complete graph as you mentioned. Yeah, thank you. Is it clear? If you remember the definition of semantic 2, it was A react, B react only, or both reacts only, or none reacts in optional cases. Optional in some definitions. And then if I ask you the question, I give you this state machine and ask you, can A and B be simultaneously present, the output, not the component, the small a and small b? But why not going from S? You said from S1 to S3. Okay. 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 But so the answer is no. Okay. And there is other no here also. So do you agree? Exactly. So the answer, the correct answer, it depends on the semantics. In semantic two, it can be, but in semantic one and asynchronous, it cannot be. Right? So it depends on the semantic, and it's possible in semantic two. Yeah, thank you. So here is the answer. It depends on the model of computation. Synchronous, no. Asynchronous interleaving, which is semantic one, no, because this is the semantic, and as you can see, it either A or B on all the transitions. However, if you allow semantic two, two is yes. because I'm allowing the transition from here to there, and from 1 1 3 to 2 4, 1 1 3 and 2 4, I am still outputting true and nothing. But if I stay at S2 and S3 and then go to S1 S4, right? If I stay at S2 S3, exactly, and then take this transition and take this transition, exactly, from S2 S3 to S1 S4, like this. So semantic 2 is possible to have the simultaneous A and B, small a and b as out. The reference, yeah, it's confusing to call all of them A and B. One is big and one is small, but yeah, you understand, right? So this is the answer, and you can add the semantic 2 is yes. And for asynchronous composition under semantic 1, the symbolic definition of C has the same definition of states, inputs, outputs, initial state, but the update function becoming for semantic 1 either A react or B react. So one of them, the output is absent in one of them. And then as we did before, there is a shared variable where we added the variables from finite state machine to extended state machine. An extended state machine has a local variable that can be read or written as part of taking the transition. And instead of having separate state for each value, you can have variables. It will result in a simplified state machine, but it takes some time to think about it. But the result is much simpler. So sometimes it's useful when composing a state machine to allow these variables to be shared among a group of state machines. I think you have similar example in the assignment of the 2 server example, if I remember correctly. So you consider 2 servers that can receive requests from a network, and they are side by side. For example, each request requires an unknown amount of time to service. So the servers share a queue of requests. If one server is busy, the other server can respond to requests, even if the request arrives at the network interface of the first server. So it might go to server A or server B, and it's unknown how much it will take, and they share a queue of requests. And we can define a shared variable pending count that counts the number of pending jobs requests. When a request arrives at the composition machine, one of the 2 servers is non-deterministically chosen to react. assuming asynchronous semantic one. So it's asynchronous semantic one, which is interleaving semantic. And this is the state machine. Can anyone explain? Exactly. It depends also if you are done, you might check if the queue is empty or not. So if we have two states at each server and the request goes to both, if it's idle and get a request, we will go to serving. If there is no request, no new request, by request here it means new request. If there is no new request, we will continue in serving. If there is no request and the pending is greater than 0 and we are done, we output done and decrease the pending. If there is a new request and we are done, we take it and continue. If there is a new request we are not done, we add the pending, we increase the pending by 1. And if we are serving and there is no new request and the pending queue is 0, so we output done and go to the idle. If we got a request, we go serving. If the pending is greater than 0 and there is no request, we decrease the pending by -1 and go to serving. Is it clear? And the same state machine is repeated down. And the request and the done are pure signals. What pure mean? What does pure mean? Exactly, thank you. It's either present or absent. The pure signal means that. Yeah. Which one? From idle to serving? Yeah, if you are at idle and you receive the request, you start serving the request. You mean this one? Is it clear? Okay. So the difference between both, that one has pending greater than 0 and one has no pending. The difference between the two transitions. Yeah. Okay, thank you. And then I would like to define the cascade composition, which means the output of machine A feeds the input of B. This style is called cascade or serial composition. And in synchronous composition of cascade structure, a reaction of C consists of both A and B. When A reacts, when A reacts first, produces its output, if any, and then B reacts. However, we look into this cascade in the synchronous fashion as simultaneous and instantaneous. It's not like, oh, we got the output and then we wait for the next step to get the input and then output. No, they happen at the same time as it's synchronous. It's zero time between them. So here the states input, output, update initial state of the composition, and the output port of A is connected to B. And then as a bonus question, can you give the semantics of the cascade composition assuming synchronous composition? So cascade and synchronous. So 1, 3, self loop, okay. AB or AC? Okay. Oh, so you mean, sorry. And here B also? Exactly. So S2, S4. Mm-hmm. You want to add anything? What about 1, 4? So you mean it's there, but it's not reachable. Okay. Okay. Mm. That. Okay, thank you. Do you want to add something? You mean the other states? You can do both and write that the others are non-reachable and I don't write them. Yeah, sure, yeah. Do you agree to this? No, sorry, this is A. You agree to this? So we need cascade and synchronous. And they happen at the same time, the cascade. What do you think? If we are at 3, if we are at 1 3, and then, but you need to look at the semantic at all. So the input is A. So what's the status of A? Yeah, if you would like to do semantic, you can get rid of B, right? It's an intermediate step. But you can consider not B also. But what's the meaning of not B? B is absent, right? When this will happen? When A is absent, the B will be absent. Do you agree? So let's see the answer. It's here. So 1, 3, 2, 4, and 2 non-reachable states. So let's understand it. So they are, so first the answer is correct. Thank you. And the other two remaining states are non-reachable. So let's go through it. We have, if the states are the Cartesian product again of the synchronous, which is 1, 3, 1, 4, 2, 3, 2, 4. Right? This is the Cartesian product between the two states. And then if you are at 1, 3, and you received A, what will happen? If you are at 1, 3, and you received A, what will happen? B will fire, right? Exactly. A will fire, A is there, so B will be there. And then given that they are synchronous and cascade, they are happening at the same time. So C will fire immediately. That's why I wrote here AC. So it's not in the second step. So A will fire B and B will fire C. Clear? Okay, great. And then if it's not A, it means not B also. Do you agree? So it means I will go from S1 to S2 and S3 to S4. Because not A means the B will not be there. And then not B, because the B is not there, I will go to S4. That's why I moved on not A from S1, S3 to S2, S4. And then there are two non-reachable state. First, from S2 to S4, if I got through, I will return back on both sides. And they are happening synchronous. So both of them respond at the same time. So I will return upon true to S1, S3. And then if we consider S1, S4, if I am here and there, and I received A, so S1 will become still S1, right? Because it's A. And B will fire, which means, 1 second, if I'm at S1 and S4, it's not reachable, as I cannot reach this state. However, if you consider it and would like to draw it, you will have S1 and you fire A as input, and B will go away, and you are at S4. The A considered true or the B considered true, so you will return back to S3. Did you got why you didn't output C in this case? Because I am here. I am at S1 and S4. And I got A, so B will fire, and B is considered true. So true means I will go to S3. Is it clear? Okay, great. Clear for everyone? Okay, great. And then if I am at S1, S4 and I got not A, S1 will go to S2, not A, and B will not fire. B will not fire, it's still true. True means it's activated upon all cases. So that's why 4 will become 3. So I went to from S1, S4 to S2, S3, and upon true, the 2 will return to 1 and the 4 will return to 3. Is it clear? Okay, great. So let's read the text. It's clear that the reactions of the two machines are simultaneous and instantaneous. This happens where from S1, S3, the A will fire, B will fire, C will fire at the same time. The composition C don't pass is which occurs when the A is absent. The composition C don't pass through S2, S3. He means that you are at S1, S3, and then you would like to go to S2, S4, and you received not A. It happens immediately that you move to S2, S4, because the A is not there, the B is not there, which means this will be executed immediately. And S2, S3 are not reachable. S1, S4 is not reachable. Is it clear? Okay, great. And then the example time triggered pedestrian light. Here it's a pedestrian light. So we have the pedestrian green and the pedestrian red as pure signal. And we have the B count. It's not hybrid automata. It is a finite state machine, or it's extended state machine because it has variable. And it keep counting until it reach 55. And then output pedestrian red and go to red. Otherwise, if it got signal red means from the car. If the car is red, you can be green for the pedestrian. Is it clear? So the light stays green for 55 seconds, then goes red upon receiving a signal red input. It repeats the cycle. And then if you remember the time triggered car light, we discussed this state machine many times now. If you are in the red and the count will increment, this is the car light, not the pedestrian light. And then if you reach 60 count, you go to green. If the pedestrian shows up, you go to bending and decrease. If the count didn't reach 60, if it reached 60 and the pedestrian shows up, you go to yellow and so on. And then to connect both, I will take the signal red from the car light to the signal red in the pedestrian light. If the car showing a red, it's green for the pedestrian. Do you agree? And this is called the cascade, if you remember. And as an exercise, you can draw the synchronous cascade semantics, which will be horrible like this. So we will have red, green. Where are the non-reachable states? Exactly, it cannot be green for the pedestrian and for the car. Right? Green, green, and exactly, I cannot give yellow for the car and green for the pedestrian. And I cannot give bending and green for the car. So as you can see, there is from the starting point, there is no arrow in this direction. And the state is car light and then pedestrian light. So the first argument in the state here is this is the car and this is the pedestrian, as written here. So you can remove the unreachable states and don't draw it and write that I didn't draw the unreachable states. And you might have general composition, which is side by side, for example, and cascade in the same time. So the A1 and A3 are cascade, are side by side, and then A1 and A2, A3 and A2 are cascade. Also B and A2 is cascade. And if you remember, if the feature is for B, it means it holds for A3 and A2 and A1. So B and A2 are cascade composition with feeding event to A2. We can call also B and A2 are cascade in the opposite direction with A2 feeding the events to B. And cycles like this are called feedback. So this feedback. Maybe I can stop here as I feel that you are out of service. Okay, I will stop here and continue next time. Thank you. Thanks. Sorry? Yeah, exactly.